So today I'll be talking about, there's the finalization steps of the deep water module in FUNWAVE. So right now we're in sort of the final sprints and trying to tie up a lot of the loose ends. Today I'll be pretty much covering three topics, sort of the development of the deep water module, some new sort of applications of the tide and surge model, and some other applications of FUNWAVE. So for the discussion of the highly dispersive module, we'll sometimes refer to as the deep water module. I'll give kind of a brief overview of the key differences in the theory and numerical scheme in this new model compared to FUNWAVE. I'll also show some preliminary test cases and improvements with this new model in this model. So on the right, we sort of have the documentation being developed. It's still in a work in progress, but there's a link above. It's discussing some of the theory and details and the definition of the driver files and the inputs into FUNWAVE. So I don't want to get too much into the mathematical details, but this is sort of the new module sort of based on the 3D Navier-Stokes equation, the conservative form. In contrast, FUNWAVE is more built on the 2D form. So what do I mean by that is that one key difference is we now have this new sort of a new spatial derivative. But the thing to notice here is we're doing this derivative with sort of this new quantity of surface flow instead of the typical z direction. So what this results in mostly is that there's some new terms in our equation, and also there's now a fourth equation for the conservation of momentum in this new sigma coordinates or surface flow coordinate. Similar to before, FUNWAVE, the original FUNWAVE is sort of a depth integrated equation. However, because we're now doing this sort of new sigma coordinate, surface flow coordinate, these integrals are now sort of integrals with respect with a sigma coordinate. To kind of show how this idea is one issue with sort of FUNWAVE, the single value problem. So when you sort of have on the left figure in the bottom, when you start having waves overturning, you sort of don't have a single value to describe that wave for a single sort of x transect. So what kind of the surface wave formulation does is sort of simplify and linearize this sort of overturning wave. So one key reason why we try to go with this approach as opposed to sort of a volume of fluid method is that this method is still like an order of magnitude faster than the volume of fluid method. So sort of a key difference, another with the numerical scheme. So we kind of adapted a new two-step projection method. So the first step is the hydrostatic predictor phase, and this is analogous to sort of the original FUNWAVE equation. However, now including a sort of surface flow technique, there's a sort of a new phase, the non-hydrostatic corrector phase, which involves solving a Poisson equation. This is where the 3D z coordinate or sigma coordinate layering comes into FUNWAVE, into this new model. So I don't want to bog you down too much with the math details, but sort of in that mess of equations is sort of the star variables, which are the predictor phase variables, and the non-star variables are the new dynamic pressure term. So another change that we've made to this FUNWAVE is if you look in the right figure, originally these methods such as uses such as NHWave use a 15-point difference stencil. So that's these black points plus these gray points. However, we've reduced that using the partial implicit finite difference stencil, which just reduces it to 7 points, the 7 black points. So one benefit of this is there's not much loss in accuracy, but the numerical scheme is up 50% faster or more efficient. So moving on to sort of some of the preliminary testing we've done with this new module. So the first test is we did sort of a simple standing wave experiment with different KH. So on the right figure, we have on the x-axis, we have the number of layers, vertical layers, and the y-axis, we have the relative numerical error. Here we're trying three different cases, KH equals pi, which is sort of the current limit of current version of FUNWAVE, and the 2 pi case and 3 pi case. So you see that the layered model does pretty well where, in maximum we have 5% numerical error, but even the sort of 4-layer method for a 2 pi case only has sort of a 2% error. So these preliminary tests shows that we're resolving sort of dispersion equation well. So we're handling the highly dispersive waves accurately. So one thing to consider is now this new extra computational time. How does this affect FUNWAVE, computational times? So one thing to note is that similar to other models, this sort of 3-layer models is 8 times slower than the original FUNWAVE. So there is now a considerable extra computational cost. But if you look at the right figure, here we have the number of vertical layers on the x-axis and the normalized computation time. What I mean by that is all these times are normalized by the 3-layer computation time, hence computational time of 1. So the good thing to point out here is that increasing the layers doesn't increase computational time too much. Even if we triple the number of layers from 3 to 9, it's still less than double the computational time. So about 70% more computational time. So even though this is more expensive than the FUNWAVE model, adding the additional layers and increasing accuracy doesn't come with too much of an extra computational cost. So one thing to consider now is one motivation for doing some of this work was sort of ship wakes. So here this is very similar to the previous FUNWAVE model where we use the same sort of pressure source configuration of the model, where here L is the length of the vessel, W is the width of the vessel, and here this alpha 1, alpha 2, and beta are sort of shape parameters. And you can kind of see in the animation how these shape parameters affect the shape of the vessel, the pressure source. And I guess with this beta parameter, it's just one parameter that controls the size of the vessel from bow to stern. And the bottom right figure, we just kind of have an example of the shipwake vessels generated by this pressure source in the new model. So I said one reason was we went down this path was that there's some deficiencies in modeling ship wakes. So here in the bottom left, we have sort of a spectrogram of the ship wake chirp. The main thing to note here is this horizontal white line. Everything above that, that's the KH equals pi. So everything above that is where FUNWAVE is inaccurate in modeling waves. So 3 things to note here. There's a main divergence chirp, which is the red plot on the right. There are these fake high frequency energies due to modeling errors for KH, which is the green plot on the bottom right. So I'll get more of this into the next slide. We're calling these fake higher frequency because these are a result of the numerical modeling errors in FUNWAVE and not the physics. And also to kind of show how where the physics is not being met properly is the higher harmonics. So that's that purple box region. If you analyze the sort of main divergence chirp of the ship wake, the frequency is about 0.25, so these higher harmonics are not accurate. And then you kind of see the right figures are decomposition. So this gray line here is the blue, the red, and the green line added together. So we can see there's sort of this fake higher frequencies distort the main time series divergence chart. So kind of highlight these differences on the middle figures. We have the same original plots from the original FUNWAVE, and now we have the same plots, but now for the 6-layer. So as I mentioned before, there's why I was calling these sort of higher energy, higher frequency energies fake is, well, as we go to the higher model, they disappear. Also, as I mentioned previously, these sort of higher harmonics are distorting the signals. So you see here from the left to the right figure, the main time series, the main chirp of divergence chirp of the ship wake is not heavily distorted by the higher harmonics. I said we're not more accurate. We're not actually more accurately capturing the higher harmonics because, as I mentioned before, the divergence chirp is about a frequency is about 0.25, and this second harmonics is about 0.5 hertz. So, even though we're accurately capturing these high harmonic energies. So now on this next slide, we will kind of, as I mentioned, we'll kind of see what the impacts of adding new layers. So one thing to notice is as we increase the number of layers going from left to right, going from 3 to 12, we can see the higher harmonics in the green box are more properly resolved and have an increasing energy. You should also note in the leftmost figure, the 3-layer model is more accurate than FUNWAVE and does sufficiently well as we no longer see these sort of fake higher harmonic energies. And while the sort of second harmonics are weak, they're still present. Furthermore, if we sort of start comparing the 9 to 12 layer case, we see that these second harmonics are pretty much kind of converge to a single magnitude. So where it seems at this point we're properly, at least within the model, resolving these higher harmonics with the 12 layers. So going beyond 12 layers at this point, in this case, the receipt would not add too much. So this part, it kind of concludes the discussion of sort of the deep order module. So we've completed the code. There's some revisions still need to be made left, but we're some of the results so far are promising. So as mentioned before, we have also added sort of a tide and surge module into FUNWAVE as part of this work unit. This is basically, we've added a forcing term on the boundary to add sort of varying tidal levels and velocities. So in this case, we've done a 24-hour simulation at FRF facility. And in the left figures, we kind of see the left figures is sort of the wave height at a 10, 3-hour and 10-hour intervals. A thing to note here is the same color bar is used across all these plots. And here you can see sort of the mean water level increasing in the 3 hours and then decreasing to 10 hours. So you have, we're modeling the waves riding on top of the tidal currents, tidal waves. Similarly, in the middle figures, we're plotting the sort of braking signature. And similarly, we can see how the braking signatures change as the water level changes with the tide. And to kind of analyze this a bit more in the right figures, you see here, we're plotting some of the station point-wise time series data, going from the top left, from the top to the right, bottom left to bottom right. We're going from onshore towards shore. We're going towards shore. So we can see clearly that we're having both the wave signals being picked up and the tidal wave signal being picked up. And similarly, in the, I guess in the bottom right figure, this gauge or station's on ground, or as a ground at low level is dry at low level at low tide, but above water at high tide. So we see that signal being picked up there. So some other applications that's we have the tide module has been used is the University of Delaware as part of the Environmental Security Technology Certification Program has been combining FUNWAVE with other numerical models to predict sea level rise in Norfolk as part of to protect military installations. So here I'm kind of showing with the link at the bottom of some of the material they have out there of showing interactive maps with different cases. As you see, I'm selecting different cases here of different water levels, scanning the map, and just viewing the data they have presented with FUNWAVE and other models. Also, as we consider tide and currents, we're now considering simulations on much longer tidal time scales. So one other need that is required for this is now that we also need to consider time varying spectra. So one other new addition that has been made to FUNWAVE is to add this time varying spectra. So the top right, top left figures, we have just examples of sort of one spectra input and another, and I'm going to the right, there's just a different spectra input at some later time. So in FUNWAVE, these are just two different input files that you can put in, and FUNWAVE will interpolate the spectrum and dynamically vary the wave the spectrum as the simulation continues on. So on the right sort of figure is sort of an example of the changes to the input file to add this sort of new time varying spectrum. And the bottom link, and the bottom, this work is currently in preparation for a journal publication. And as with everything in FUNWAVE, the wiki will have information. There'll be direct links to all these new features in the bottom. So with some other additions we've made to the FUNWAVE model, to the wave maker, is we've added sort of two component wave generators. So to include some infragravity type waves into FUNWAVE, into the wave maker. So here we have the example of Roy Moore and the Kwajalein Atoll. But here we see the waves coming, and I guess right now we see a big wave hit, this sort of input static surge. And this new wave causes massive flooding and overwash. So some of this work was partially motivated by an event in the current location. You can see this picture here where they had sort of a rogue wave, or what it was believed to be an infragravity type wave hit, and that caused massive flooding in their region. So similarly, as you know, with this highly dispersive deep water module, as we trying to expand the capabilities of modeling vessel wakes, we also need to account for other deficiencies. So one sort of shortcoming in FUNWAVE is we don't, in the vessel module, there's no ship propeller effects. So there has been some new additions to include this. So in the top left, there's sort of a diagram of how this is proper effects are modeled. These bottom figures, there's comparison between sort of the sediment concentration in the water column in the no prop case, no propeller effects case, and in the prop propeller case. And in the right video, you have a comparison. At the top is just the surface elevation, the case without propellers, and the case with propellers. The one, I guess, one key benefit now here is these results are more analogous to what is observed in more realistic 3D models. And I should also mention this work is based on a recent paper where the theory of this model was developed. I guess another new feature we have added in FUNWAVE, while not directly related to this project, is a precipitation module. So what this basically adds is sort of a new input for time and spatially varying input flow rates in terms of millimeters per hour. And this is added into FUNWAVE as in terms of a source term in the conservation of mass equation. So these are still preliminary results, but they look promising so far. So in the top left figure, we have the bathymetry layout, and in the bottom we have the flow speed and vector field of velocity field. With on the right, we sort of have a blow up of that. So while this probably requires more validation, its results so far are promising of showing flow caused by this precipitation. And I guess to finish up, there's various papers. There's various technical notes and papers currently being submitted or in review on the different modules presented here, on the different capabilities presented here. And I also like to mention that FUNWAVE's, we're having two sort of mini workshops in the coming months. A beginners workshop the 21st, and a specialized topics workshop on the 11th of August. And there's a link to the signups at the bottom.